Okay, this is a very quick example of an idea that I have. Okay, so this is the Boids algorithm. I don't remember exactly right now, but I've got to look up the place where I got this original idea from. And the idea comes from the fact that instead of mapping Boids onto an XYZ plane and displaying them, this guy decided to make art that is sort of living by creating a by creating a well, just by imagining the data in a different way. Okay, so he decided, heck, I can just map these out, because in the original Boids algorithm, your neighbor, your closest neighbor, is actually a set object. It's always your closest neighbor in the Boids algorithm, because it's you're linked to it right at the very beginning. This is sort of what we're doing. The same concept is being used in moving around these perceptoids. I'll do a video of a naive one here in a second, or I'll load up the naive stuff here. But the idea is this. Okay, now I've modified this guy's algorithm, and you see how this is sort of like well, it's really sort of looks like some sort of a star field or a star cluster or something like that, of constantly changing colors, right? But all it actually is the Boids algorithm, and what I did to give it a little bit more, I don't know, pizzazz, whatever you want to call it, is this. I'm going to reset, right? So that's when it restarts, and it goes back into the setup for this is when it actually, like, okay, now it's converged, basically, right? Now it is a mixture where I've created this thing that's called easing, right? Now, to do three-dimensional Boids, what you have to do is you have to ease, or sorry, to do three-dimensional Boids, you have to do the Boids algorithm on the variables for all three dimensions when you're calculating the velocities of the vectors of these little Boids, right? And remember here, each Boid represents a cell. You see how it's a little bit pixelated there? That's because each of those are cells, and each cell represents a Boid, right? So obviously they're here, they're exchanging, they're looking at their neighbors' velocities, and they're changing their colors based off of those velocities. And I even added a system so they could look up and down. This is a project that I did a long time ago, and I opened it up because I was trying to get this guy's magic vector math, is what he calls it, and so what I've added to it, and why it looks like this instead of a normal Boids algorithm, because his output, because his output was nice, but it was very it didn't have much dynamic spontaneity in it. You see how there's like these little points of color that just pop up, and then they sort of like they merge into the background like a wave, right? And they get propagated all the way through the two dimensions, okay, X and Y, that these guys are lined up. They're lined up in a grid, basically. And so these little points, these are velocity easing values, right? And if the velocity eases, it has a top, so that it can't go above R255, G255, and B255, and it can't go below 0 on all three values either. So you never actually get something that's outside of the space which they exist in, so to speak. And so now, the interesting thing about this is that what I did is I made I made this like the easing system. The reason that easing is not just a uniform thing, and some points are faster velocities. You see how they show up as lighter? That's because they approach R255, B255, and G255, i.e. white. They approach white very quickly. And then they hit white and they bounce off of white. I basically just reverse the vector. So they bounce off of white, and that's how you get this this ripple effect throughout the neighbors. And the ripple effect is something that naturally just happens in the Boids algorithm, but you can only see it if you do something like this, if you do this weird easing thing that I do. And I set it up so that the easing is a map, and the same easing map itself is another dimension of the Boids algorithm. So it's actually a 4-dimensional Boids algorithm, which the 4th dimension is a velocity dimension, which is attached to all other 3 dimensions, R, G, and B, by that velocity, right? Now, there's easing, and then there's easing, right? So if you controlled easing, then you could create all sorts of different, like literally, the way that I have this set up right now, it's very stabilized, right? But if you could control easing, you can get all of these different results that are completely unpredictable, because this is an actual dynamical system. It's something that it's chaos theory in its purest form, right? The easing also has this nice effect. Okay, now, so one thing about this is that I decided that it would be nice to be able to sort of paint a picture on the Boids, on the 4-dimensional Boid space. So when I use my mouse, I'm gonna go off screen there. Okay, now it's following. Okay, right now I just right-clicked. Okay, and when I right-click, what I do is on the Boid that is under my mouse, I create a pixel that has a maximum easing value, and what that does is it makes the Boid go crazy, and it like tries to basically follow its nearest neighbor, but it follows it way too far away, and then it has to go back, and then it has to go back in, and then it has to go back in, and all the other Boids have to adjust in order for this to happen, right? Because their nearest neighbor is that guy. So his nearest neighbor goes, whoa, I gotta go up, and the other nearest neighbors go, oh, I gotta go up too, right? On all of the axes, on all of the axes, right? Because easing affects all of the axes. So when I move, on mouse move, I have this set up. So when I move my mouse, I can sort of just, the colors are not generated by, these colors are not generated at all by my mouse, or by me, or anything like this, or even by like some sort of randomized color picker. It's actually generated by the easing. That's all it is, because the neighboring Boid is so far away in each dimension that it has to adjust in each dimension at a specific velocity, and that changes the intensity in that dimension, in which we're talking about the 3 color dimensions, which easing affects. So I've created a 4-dimensional world that you can see through a 2-dimensional window of Boids, in which the 4th dimension, like time, for instance, in our dimension, is a dimension that dilates and changes, or dilates and contracts the space around it. Okay? Basically. it's like it creates a sort of gravity bomb or something like that. Just drops it right under the pixel when I move my mouse, right? And all of the other things that are around it are attracted to it and repulsed by it by the same time, so they wave, right? Now I have this other thing where if I just use a left click, I'm gonna right click again, or actually once I left click, this will go away. So when I left click, I can select any of these colors that come up. Let me just click off. Okay, I can select any color that comes up and do that. I just sort of drove the mouse up. I clicked and dragged the mouse up over these colors. What I did is I set those voids as static, right? Which means that no matter how the other voids around them move in the three color dimensions, they have to adjust for this other void, but their other neighbors are pulling on them too. So they sort of, the ones that are very close to the static ones, they go crazy. They have this very random behavior to it. They generate these random colors, right? The ones that are further away are affected by all this randomness, but only to a degree in which propagates through the entire two-dimensional matrix, right? It's like, I don't know, maybe it has something to do with fluid dynamics. And literally this just keeps going on and on and on. Right, now I generated some green. Now let me just click in there and put this blue over there. I like this orange stuff over here. I'm gonna do that. And that darkness over there, I clicked on that. Right, now, okay. You see how there's now a specific pattern that gets set in this, there's a specific pattern that's set now in the world of these voids. There's specific voids which will not move, okay? And that constrains the movement or the propagation of any wave that's being propagated through their space. It's like how matter or the change of the medium, for instance, going from I don't know, water or something like that, or matter itself changes the way that electricity propagates through it, for instance, is another way to look at it, right? You see how this one right here, that one right up there, that turned red? It's going all crazy. Its nearest neighbors are this dark color, and everything else around it's trying to turn into these other colors, right? So if I continue drawing, I'll just keep this blue over here, and oh, there's a little bit of green, like greenish blue. There's some green up there, and then if some green shows up over here, I wanna show how green propagates through the map, right? I want to sort of control how green propagates through this map of voids. So I'm going to find something that's yellowish or green, because yellow is high on the greenness, right? Anything that's orange that you see here, orangish, or right, so I've got this orange over here, I've got these like bluish colors in there. Oop, there's some green over there, there's some green over there. Okay, now as you can see, oop, there were some little green points that propagated through there, so I've tried to grab those points, and now the ease on those points is also set. So the ease dimension, these points basically constrain and affect all three dimensions. Ease itself, like time, for instance, and I guess it's been shown recently that gravity is the wave, so to speak, of time. The wave frequency of time, or something along these lines the scientists are getting to. So basically, okay, now you can see how these static green, they're static on all 4 dimensions. They're static on R, G, B, and E, which is E's. Okay, so not only do the RGB colors around them are forced to be green or close to green or always approaching or going away from green, right? But the E's around it is also, in 1 dimension, it's also going up and down, trying to approximate itself to the same E's as the set pixel, or as the set, well, it's not a pixel really, it's a Boid, right? To the same E's as the other Boid. Okay? And remember, E's affects the propagation of colors basically is affected by the E's. Right? So anyway, now as you can see, I've got green propagating through here quite nicely. We've got some weird stuff going on over on the left with this bluish stuff propagating itself next to green to try to adapt to the different other colors that are just trying to get into this whole scene. Now remember, I'm looking at it this way, and that's the key, is that the actual final color itself can be represented as an integer value or multiple integer byte values, okay, and the easing itself. So basically, this is something along the lines of a dynamic system which approximates itself to a neural network that's given feedback by me clicking on something and saying that I want it to stay, right? i.e. something like long-term memory as opposed to short-term memory. The rest of the time, this entire imaginary space is just it's just fluctuating, but it's not necessarily fluctuating now at some sort of a random, uncontrolled way. It's fluctuating in a way that respects the boundaries set by this long-term memory. Just like beings try to respect the way, try to respect the lessons that they've learned about life and how it affects them, right? So I'm glad that I pulled this back up, because this has a profound importance on the perceptoid system, because obviously this is 4-dimensional, so E's could easily be time or anything along those lines. I could just set time to E's, and then basically what I'm thinking about is a couple of things. First thing is setting the memory, setting the static Boids, right? Those static Boids also could represent things that are static or semi-static in a video, i.e. not moving or moving. And so if something is not moving for a long period of time, for instance like objects in the background, those objects could become set. Then the area which is, if the z depth of those objects can be gotten, we can do full 4-dimensional math on this and make it so that basically it creates a dynamical map representation of all possible nearest neighbor configurations or something along these lines. It represents that given a specific scene. Thus, the scene could probably be represented by the sets of pixels which are set And then if those pixels are set, because this system is just mathematical, there's no randomness involved in it, it just seems random because we don't understand. Well, we can only kind of understand how it works, but we can't actually do the math of this entire thing and prove that that's how it works. So the thing is this. Okay, yes, we can do the math of the entire thing and prove that that's how it works, but literally you can't look at this and be like, oh yeah, I knew that was going to happen, is what I mean. But you can sort of approximate an idea of what you think is going to happen if I tell you how it works, right? And that's sort of what we're trying to do here with the perceptoids, is give them an idea of what might happen given a very small set of factors. For instance, the perceptoid is up on the XY point space, and it's it has points that are in its local neighborhood, right? And we can get radial density mappings. And these radial density mappings are very, I've already worked out the math for it in my little notebook here, with drawings and everything, but I'm not going to show it just right now. But I call it, in the notes, I call it four-directional neighborhood distribution, or density distribution comparison. And I basically, I use a radial map of density. Like imagine, you know how this is pixelated? Basically, imagine that a circle has a whole bunch of circles going in towards the center, and then and then it has a line drawn from the center of it to a whole bunch of different points, like a pizza slice, but radially cut pizza slices, right? So you've got your radial distribution, or radial density distribution, which is can be based on angular slices using the LOD tree system that I've put together. And so this means that the system can be fully coded and fully, I don't know, generating data about its environment and what's going on inside of the Boid itself, right? So it's quite a I think it's quite a good marriage of two different algorithms. Besides that, I need this Boids algorithm for the Boids cohesion, alignment, and separation. This is going to be great. So I'm just going to do the cohesion, alignment, and separation first, but then I'm going to start to look into the memory of each of these things being a sparse, well, not really sparse, a density map of local inner and outer neighborhoods and how they relate to each other. Right, so this density map changes over time, just like these guys do in this Boid space, in this 4D Boid space. So if they change over time, then we can easily map, for instance, do the algorithm backwards, so to speak, do the equation backwards, so that instead of outputting colors, or use it, or actually just use what it is, when specific colors are set, the probability, or when specific densities are set, the probability of other densities around it being a specific way are within a certain number of iterations of the Boids algorithm, a four-dimensional Boids algorithm. And as the system goes forward, there is no number of iterations that it has to do it. It can just continue with the flow, a three or four-dimensional flow analysis. If the algorithm itself has a smart way of putting points onto it based off of specific actions that are known or known to be being recorded at the time inside of the perceptoid, well then yeah, you're literally looking at something that's going to be, who knows what it's going to be. Might learn to follow specific things very well. Like, because technically each perceptoid can have a full-time memory which just exists as one map, one radial density map. Angular radial density map, if you want to call it that. Well, it's a radial density grid. That's what it is. Sorry, it's not a map. It's a radial density grid, which is technically a map, yes. Anyway, so basically the idea is using this modified Boids algorithm as a trainable neural network. And these actual values of these Boids that are set can also be changed, because all the set Boids are on a specific array themselves, right? But a number of different possibilities can happen given this fluid dynamics artificial life system. Let's see. Let's see if I can just constrain this thing all the way. So I'm going to make a line all the way through it that's just some random colors that are behind it or whatever, right? Whatever was there at the time. And you might notice that there's like these spiraling effects that happen, waves and spirals, just like in physical fluids. Set some more stuff up. There we go. Like that. I'm gonna try and wow, that's one near the top was pretty. It's pretty intense because that green is right there, right? So as you can see, this line that I just drew towards the top is constraining that green inside of a space, because it's almost the opposite of green. Now the green can travel around it because the green is a fluid, right? Like, imagine the colors are mixtures of fluid in a two-dimensional fluid space. And even though the velocities of these Boids that are right on the, like that red one that just showed up and is changing colors now, all crazy. Those velocities aren't even calculable by this equation. And I chose green because green is a RGB value, right? So it's a full, like literally, this is all just working with prime colors, right? Red, green, and blue. So really the prime colors are the only pure colors. When something is fully just one color, like green, red, or blue, any one of those three colors, it is the absence of the other two colors which makes it that color. Anyway, I'm going to stop freaking you guys out here and get back to coding. Let me see if I can make this warmer spot larger. Alright, now see that warmness, well, what I call it warmness because I'm a human, but it's creating a different flow now of that magenta-ish color, and it's creating some weird bouncing with green, right? Green is sort of bouncing in and off of it from the different directions that green is propagating from. And this is a pretty large collection of Boids. I'm really talking about something way more simple, like the number of neighbors within the radial distance from within the radial area of a centroid of a perceptoid. So that's not going to be the size of an entire screen. And it's going to be great. It's going to be monade, so to speak, pixelated, radially pixelated. So that will make it. Anyway. More on that later, because at the end of the day, it's not really a neural network. It's just using a dynamical system to represent the flow over time of the outcome of the flow over time of a real thing projected onto a two-dimensional plane. Right, so since these two-dimensional hyperplanes, I just read in a little article on Wikipedia that since two hyperdimensional, if going up in planes, going up in dimensions is easy as long as the dimensions are not attached, right? This system, though, technically the dimensions are attached, but they're all only attached to the E dimension, right? All of the rest of the dimensions are technically unattached from each other. If you turn red off, green off, or blue off on the system, which I've done before in tests, the other ones will propagate regardless of them. You see, the combinations of those colors make other colors which we have named. So we recognize those colors. The reason why it seems to us that this is some sort of a, it's this weird color mixing system and blah, 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 blah. All it really is just these three different colors superimposed over a two-dimensional plane. So 3 dimensions superimposed over a two-dimensional plane that are propagating by themselves. The only real thing that affects them is the ease. The ease is also on another dimension by itself, propagating throughout, just like the rest of them are. Except that the rest of them are right. They need ease in order to propagate slower or faster through. The colors need ease to propagate slower or faster through a specific XY imaginary void space. And it really is imaginary because this guy used his imagination. And then I used my imagination. And we all imagined stuff together. So, right. Right, so I'm trying to pull red up a little bit, right? So where I was going with that is that these perceived colors like orange, magenta, cyan, whatever you want to call it, purple, all of those colors are, these colors are actually, in this world, those colors are actually just a, I don't know, they don't really exist. They look like that to us because we're projecting all three of them onto a two-dimensional plane at once, and for us, when you mix those three different frequencies together, you get a different frequency. So we see that, and what we've done is, in our world of color, we've taken those frequencies and we've categorized them. You could say that we've automatically generated a map of frequencies on a three-dimensional cube, right? The three-dimensional cube of color. And we've taken those frequencies and we've said, hey, when this one's here and this one's there and that one's there, it's this color, right? We didn't really see that though to begin with. So the thing is this: we just saw them as different things, right? Because guess what? Our eyes do the same thing. They overlay the colors, like the frequencies of light that bounce off of each other and then bounce through other surfaces and onto our eyes is the physical conception of that. And as you can see, this thing is running pretty fast, so with much less neighborhood to deal with and smaller space, this thing could be calculating in real time, figuring out where to put those dark spots, and where to put those light spots. Which ones seem to have more, pizzazz.